Today, I want to look at an important theorem in complex numbers, the Moivre theorem. This is very simple to state, that if you take a complex number r cos theta plus I sine theta, modulus argument form, to the power n, it's r to the n cos n theta plus I sine n theta. In exponential form, it's nice and easy to see, r e to the I theta to the n is r to the n and then e to the I n theta. But if you are asked to prove this in an exam, and I have known it happen just the once, you will be expected to prove it in the trigonometrical form and by induction. So let's have a look at that. If we're doing proof by induction, then we start with n equals 1. If n equals 1, then the left-hand side of the top there is just r cos theta plus some brackets I sine theta. The right-hand side is r to the 1 cos 1 theta plus I sine 1 theta, and that of course is just r cos theta plus I sine theta. And so now we can say that the formula is true when n equals 1. Second step in induction, we have to make an assumption. Assume that the formula is true when n equals k. So we're assuming that r cos theta plus I sine theta to the power k is equal to r to the k cos k theta plus I sine k theta. The next thing we always do is to look at n equals k plus 1. So if we look at k plus 1, we are going to get r cos theta plus I sine theta to the k plus 1. And what are we going to do with that? I think that you should pause the video now and go away and finish off this proof for yourself. So pause the video, go away and prove it. Well, I assume that you've managed this, but it is here. I'll just quickly look at it. It will reappear in your notes when you look them up. So we got down to here. To the power k plus 1 must be power k times power 1. This is where I use the induction assumption that the formula works. Now r times r to the k is r to the k plus 1. Multiplying your brackets together, you get cos, I squared gives you minus sine, Then you've got I times sine cos plus cos sine. This is just cos k theta plus theta. This one is sine k theta plus theta. And so you now do have what the formula gave you, or what the formula would have given you. So the formula is true when n is k plus 1. Then you've got the finish of your theorem. We have shown that the formula is true when n is 1, and that if the formula is true when n is k, then it is true when n is k plus 1. Therefore, r cos theta plus I sine theta all to the power n is r to the n cos n theta plus I sine n theta for all positive integers by induction. Don't leave out the red bits. The theorem is also true when n is 0 or negative. For n is 0, it's nice and easy. Anything to the power 0 is 1. If I put 0 in for n here, I get r to the power 0, which is 1. cos 0, which is 1, plus I sine 0 is 0, I get 1. So the theorem is true when n is 0. It's there again. And if n is negative, I will let you read that when you look at the notes. It's not difficult. It's quite easy to see. So we've shown that the theorem, de Moivre's theorem, works for n positive integer, n 0, n negative integer, for any integer. Let's look at this example. If I want to work that out, well, looking at the two expressions there, I can use de Moivre's theorem straight away. I get 2 to the power 4 cos 4 times pi by 3 plus I sine 4 pi by 3. So that's the first bracket. The second bracket is squared, so that's times 3 squared. And then I'm multiplying the angle by 2. Cos 2 pi by 8 is pi by 4, plus I sine pi by 4. 2 to the 4 is 16. 3 squared is 9. 9 times 16 is 144. If I'm multiplying two numbers, I just add their arguments. 4 pi by 3 plus pi by 4 is 19 pi by 12. I could have done this in the exponential form. I could have started with 2 e to the I pi by 3 to the power 4 times 3 e to the I pi by 8 times, or to the power 2. Then if I work that out, I get 2 to the power 4 e to the power, just this is normal laws of indices now, plus 3 squared e to the power I pi by 4. Sorry, I've written plus when I should be writing times. E to the I pi by 4. 2 to the 4 times 3 squared is 144. 4 pi by 3 plus pi by 4 is 19 pi by 12. I expect that the second way of doing it still looks rather awkward to some of you. Even the first way is still not going to be something with which you're completely familiar, but I still think it's worth trying to get yourselves into the habit of using this exponential way of writing things. If you really don't like it, then you can get by all the time with the cosine and sine. Okay, let's have a look at another example. Well, we should notice straight away that we have a minus there. The denominator is not in modulus argument form. So the first thing we need to do is to rewrite that so that we have the same thing on the top, to the power 4, and on the bottom, if I want to write that in modulus argument form, I have to remember that cos minus pi by 6 is the same as cos pi by 6, so I haven't changed that. And sine of minus pi by 6 is minus sine pi by 6. So that means now that I have written the denominator in modulus argument form. De Moivre likes us to have everything in modulus argument form. Now, let's use de Moivre's theorem on the top and on the bottom. On the top, we get 3 to the power 4 cos 4 times 2 pi by 3 is 8 pi by 3. 4 times 2 pi by 3 is 8 pi by 3. And on the bottom, we're going to get 6 squared, because 2 times pi by 6 is pi by 3, so that's minus pi by 3, plus I sine minus pi by 3. Now you need to remember that when you divide complex numbers, you divide their moduli, that's obvious, but you subtract their arguments. So this gives us 3 to the 4 over 6 squared is 9 over 4, cos 8 pi by 3 subtract minus pi by 3 will give us 9 pi by 3, which is 3 pi. I sine 3 pi. Cos 3 pi, you shouldn't take too long to work it out, and I hope you don't press the buttons, is minus 1. And sine 3 pi is 0. So there's the answer. Or we've still got to appreciate the first line that we need to put minus pi by 6 instead of pi by 6. And then we can write this as 3e to the I 2 pi by 3 to the power 4 all over 6e to the minus I pi by 6 squared. Now we don't have to think of anything other than our normal laws of arithmetic. 3 to the 4, e to the I 2 pi by 3 to the power 4 is e to the I 4 times 2 pi by 3. 6 squared e to the double the index minus I pi by 3, which is 9 over 4 e to the I 3 pi. How can we think about this last little bit? E to the I 3 pi times 9 over 4. It has modulus 9 over 4. It has argument 3 pi. Modulus 9 over 4, argument 3 pi. Well, if the argument is 3 pi, then there's argument pi, 2 pi, and 3 pi. So if the argument is 3 pi, it's here. It's minus 9 over 4. Okay, slight differences with that one. And one more example. Write that in the form x plus iy. Well, only a fool would go and multiply that out with the binomial theorem. It's crying out to be written in the modulus argument form and then use de Moivre. So let's have a look at it. If we take z is root 3 plus I, then mod z is root of root 3 squared plus 1 squared is 2. The argument root 3 plus 1, root 3 along, 1 up, that angle is pi by 6. Tan of that angle is 1 over root 3, that gives you pi by 6. So now we are looking for 2e to the I pi by 6 to the power 12, 2 to the power 12, e to the 12 times pi over 6 is 2 pi. So now we can think of something which has argument 2 pi and modulus 2 to the 12, argument 2, oh, I've got the wrong pen on, argument 2 pi and modulus 2 to the 12. 2 to the power 12 is 4096, And so the answer is just 4096. I haven't done that one with cosines and sines. I'm hoping that you're beginning to appreciate that just using r e to the I theta is a rather good idea.